Okay, so the definition of a harmonic oscillator, what we usually say, like in general physics, is that you have the net force is equal to minus k times x, where k is some constant. That's what defines the harmonic oscillator relationship. You have something equilibrium position, you displace it a little bit, it's going to have a force that pulls it back toward equilibrium, we call that a restoring force, that's proportional to how much you displaced it. It's important because that occurs in a lot of situations. For instance, you guys are both chemistry majors. And so you have your vibrational spectra. Well, those vibrations are, if you have a diatomic molecule, that's very simple. You have two molecules that have a force that's holding them together. If you pull them a little bit apart, the force is going to pull them in. If you push them a little closer, it's going to push them out. And you can linearize that as long as the motion is small, which makes it a simple harmonic oscillator. So the energy states, when you look at your vibrational spectra for atoms, you're looking at the little harmonic oscillators that we have going on there. And so if you take this, by definition, V is equal to minus the integral of force dot dx, and I should have put a vector sign over the x. So if you just take that integral, you get your answer. Minus and a minus is going to make it a plus 1/2 kx squared. Now you could have also put, instead of k, what is it, m omega squared, or that's not important. So that's the potential function that defines a harmonic oscillator. It's the basis of everything we've been doing for the last week, and we'll continue to do today. The ladder operators are operators that raise or lower the energy state. So our ladder operators are raising the energy by 1 or lowering the energy by 1. Write out what the commutator means. That's it. And finally, what are the energy states for the quantum oscillator? This is one that required a little more remembering what we had. But that was the end result from yesterday's work. Nice job on my writing. Okay, so the H bar omega, those are the fundamental energy units, if you will. And then the ground state is n equals 0. We have an energy of 1/2 H bar omega, and then it goes up from there.
And omega is the rotational acceleration?
Omega, in classical physics, omega was the angular frequency.
Yeah.
So it's frequency multiplied by, or omega is 2 pi f, so frequency divided by 2 pi. Okay. Here, it still has that basic understanding idea, but it doesn't correlate exactly because we didn't have solutions that were sinusoidal. I believe we still will have an oscillation, but we weren't finding position as a function of time. Hence, it's not exactly the same thing. Okay, any questions about the quiz? No? Okay, then let's move on. So I put it in the wrong place completely. We've looked at these pictures before. We have our solutions now. We know that we have a crazy way of creating, like for the homework, the fourth function for the oscillator, or for the wave function, excuse me. So you can, this is 0, 1, 2, 3. Well, one more above that. What was that? Yeah. Is there a problem?
No, nothing.
Okay. And so we can build those up now. We have the ability to do all of this. Now we're going to look at the analytical solution. So the analytical method is, instead of using these ladder operators, which was really cool mathematical tricks, we're going to brute force our way through it. Now, that doesn't mean it's not tricky. It's indeed very tricky, I think. But we're going to brute force our way through. So we start the analytical method by introducing new constants and variables. And you're like, why? Well, because it's going to make the Schrodinger equation much simpler to write down. We use the text uses this Greek letter C. Once again, why? Why don't they use something that we can pronounce or write, or both would be even best? I don't know why, but I wanted to be consistent with the textbook, so I used it as well. So we introduce a replacement for the position C that is linearly proportional to the displacement x. Now, I believe this comes out to be unitless if you go through, I did not, but I'm pretty sure it comes out to be unitless. And then we likewise introduce this kappa is an energy in units of h bar omega over 2, basically. So if we introduce those, the Schrodinger equation is going to be easier to write. And so I have here the first term in the Schrodinger equation minus h bar squared over 2m times the second derivative of psi with respect to x. Well, if we shift to taking derivatives with respect to c, we're going to have to use this factor of that factor twice. That is, it's going to be raised to the second power because we have a second derivative. And so that's what this term right here is. That's this thing here squared. But the beauty is, when we do that, we're going to have the m's cancel. We'll have one h cancel, and we have just minus h bar omega over 2 times the second derivative of psi with respect to c. So that's a lot shorter to write, and you see that h bar omega over 2, well, that's something that has some meaning to it. It's going to be even better because we're going to cancel it out. Go ahead.
But why are we taking the derivative of x? Like where?
Well, this here is the first term of the Schrodinger equation. And so we're taking this first term of the Schrodinger equation and getting what that same first term is with our shift in variable from x to c. So we're just changing variable. That's all.
Are we using like a chain rule in order to get to d squared d c
Yes,
squared?
yes.
Okay.
And so that's why it has two of these conversion factors, d, c, dx, because we have two derivatives we're doing. The second term, 1/2 m omega squared x squared psi, well, all we have to do is change that x squared into a c squared, except for we have this factor here again. Given the definition of c, x is equal to c square root of h bar over m omega. So x squared is going to have there. So there you have the, whoops, I didn't make the loop on there to make it c. So the h bar over m omega, when you square the square root, it's just h bar over m omega. So that's where this term here comes from. And then again, an m will cancel. One of the omegas will cancel. And you have h bar omega over 2 again. So now if I put all of this into my Schrodinger equation. My Schrodinger equation, I'll write out the regular way, minus h bar squared over 2m d second psi dx squared plus 1/2 m omega squared x squared psi equals e psi. Now, making the substitutions that we've just used, this first term is going to become minus h bar omega over 2 d second psi d c squared. The second term becomes h bar omega over 2 c squared psi. And the final term is going to be, notice if we take kappa as 2 energy over h bar omega, then energy is kappa h bar omega over 2. So there in black, I have substituted in all of our, well, the two changes we've made. And as I said, there's a beautiful thing. H bar omega over 2, h bar omega over 2, h bar omega over 2. So I can divide those out or cancel them out. And so the Schrodinger equation for our simple harmonic oscillator is now simply minus d second psi dc squared plus c, I keep putting an extra loop on it. C squared psi equals kappa psi. That is much simpler to write, don't you agree? Given that these are both the C psi and kappa psi, they're just something multiplied by psi, we usually rearrange this to the final form of minus d second psi d c squared equals kappa minus, well, let me get rid of that minus sign and do it the other way, equals c squared minus kappa psi. So that's what we're going to use for our Schrodinger equation when we do this, the analytical method. So is this non-tricky? No, we made a change in variables to make it so it's much easier to write the Schrodinger equation. This is still the Schrodinger equation. There's no two ways around it. But it's easier to write. And then when we find our solution, we're going to have to shift from C's back to X's. So here you see that's the same Schrodinger equation I just wrote out. And we're going to take our brute force method by saying, first of all, I can't solve this. And since I can't solve this, I'm going to take the approach of saying, well, let's imagine the situation where C is much, much bigger than kappa. So just like we talked about in physics today, when we had the R much, much bigger than D, if C is much, much bigger than kappa, or actually I wrote there C squared, because technically that's what we're doing, then C squared minus kappa we'll just treat as C. So I'm just going to have my second derivative of psi with respect to C is equal to C squared psi. Or maybe I should say psi squared psi to be consistent with how I pronounce the I sound in Greek. We're not, you still are not differential equations experts, so you still can't solve this, right? And neither can I. The textbook says the solution to this equation is almost what's shown here. Almost. Now, let's get a little more fundamental on this than just say almost and move on. It says in parentheses, check it out or something like that. So you guys read ahead and see that? Oh, it is. It is. This is what mathematicians have to do, apparently. So let's do this like we would before. Notice we have a plus and a minus power, minus and a plus power. So let's just try if psi is equal to e to the minus c squared, c squared over 2, then d psi dc is equal to, well, what do you do when you take that derivative? You bring down the you bring down the derivative of the exponent. So the exponent is minus, so I got to bring down the minus, c squared over 2. Derivative of c squared is 2c. So c squared over 2, derivative of that is just c. And then you still have the minus, same exponent. So there's my first derivative, which means my second derivative I have to use the product rule now. So I'm going to have minus 1 e to the minus c squared over 2 plus minus c squared e to the minus c squared over 2 over 2. There. My C's really do look like scribbles, don't they?
I'm just not following because I'm like having a hard time drawing.
It is a nuisance. It is a nuisance. When I look at this, it just looks like I've got scribbles there. If we simplify this then, that's going to be, now notice I used the minus sign for my exponent. Whether I use the minus sign or not, the one with c squared is going to be positive because I have minus c, oh, I put the square in the wrong place, minus c quantity squared. And so putting that one first, I'm going to have c squared minus 1 e to the minus c squared over 2, or c squared minus 1 times psi. Is that equal to c squared psi? No, it's got a minus 1 on it. That's why the textbook says kinda. But remember, we were doing this when c squared is very large compared to kappa. If c squared is very large to kappa, we can probably assume that c squared is very large compared to 1 as well. And so within our limitation that we've already said that we're very far away, we have very high amplitude. This is the large amplitude solution. Then this is an appropriate solution. Now, what would have changed if I'd used the positive instead of the negative exponent? Right, I'm not going to go through this a second time. What would change if I had psi is equal to e to the plus c squared over 2?
Wouldn't it just be plus 1 instead of minus 1?
Right. This would be plus here, so this would be plus, and this would be plus squared. Well, plus squared stays plus, but this sign here would change to a plus sign. So we would have c squared plus 1 times psi for the other one. And so once again, in our approximation of very large c, it's an acceptable solution. And so now we all run around, clap our hands and say, yay, we found it. But this it is only the large c solution. And we have to come back and look at, okay, since we have two solutions, it needs to be our actual size, a linear combination of the two. And notice it's approximately equal to because we had to make that drop off the this is insignificant term. But there's a problem with that, which is obvious because they have equals and one of them disappears. What's the first thing we do with our wave function? We normalize. I should put that on the quiz, huh?
Yeah.
We normalize it. Well, if you normalize it, if you look at the one with the positive exponent, positive c squared, if you go into plus c or plus infinity or minus infinity, doesn't matter which way, you have e to the positive infinity. It's blowing up. It's not normalizable. And so the only way that this solution can be normalizable is if b is 0. So that's why we have at the end psi is just equal. It must be normal. That requires that b is 0. Now we jump around a little more and we praise ourselves, pat ourselves on the back because we have a solution, and then we realize, wait, it's only the large displacement solution. If we come back to the graphs of the solutions, what we found is basically this stuff out here. We have that solution. But we don't have the solution for smaller amplitudes. So we aren't done. Not by a long shot. What we do is we say, well, if this is our large amplitude solution, we should be able to make our full solution by multiplying it by another function that is going to give us the correct result at small amplitude for our complete solution. And so Taylor says, I can make any function if I just take a linear combination of each exponent possible. So a0 times c to the 0 plus a1 times c to 1 plus a2 times c to 2, an infinite polynomial. You can make any function that ever exists as long as it's a function. Right? Functions can't have discontinuities and can't go back on themselves by making a linear combination of each power. So we're just going to say, let's make the function we have to multiply it by. This h, by the way, is chosen for a good reason. Let's just make that an infinite polynomial. So if it's an infinite polynomial, then I can put that into my newfound Schrodinger equation, and I have to take the second derivative of this function. So if psi is equal to h e to the minus c squared over 2, then d psi dc is equal to dh dc e to the minus c squared over 2 minus ch e to the minus c squared over 2. I didn't spend a lot of time on this derivative here because we just went through the derivative a minute ago. I just used the product rule. Okay, that's the first derivative. The second derivative is then going to require me to use the product rule a few more times. I had to do this twice to make sure I did it right the first time. Well, the first time in preparation for the lecture. So I'm going to take the derivative of the first term and have d second h dc squared e to the minus c squared over 2 plus the first times the derivative of the second and then I have to go to the next one, which has 3 terms. So it'll be the derivative of the first times the second and third, plus the first and the third times the derivative of the second, plus the first plus the first and second times derivative of the third. I'm going to have the product rule coming out 3 different terms. So there I took the derivative of the first thing, that's the xc. There's the second thing. And then finally the third thing. Minus, when I bring down a minus c, that becomes a positive. So that's why I just put as a positive. So I have, oops, shouldn't have put an equal sign. It's just continuing on from above. So I have a total of 5 terms. But if we look at these, we should have the ability to combine things. So this here, let's just take it by derivatives. Here's a second derivative. That's the only second derivative. Here is a first derivative. Here is a first derivative. And apparently that's the only first derivatives. And then I have 2 terms that don't have derivatives in h. So if we look up here, you'll see that we have second derivative, first derivative, and h. So let's combine the terms as appropriate. So I put the black one first. Then I'll put the terms with dh, dc. But notice this is minus c, minus c. They're exactly the same thing. So it's just 2. And I got to change that to a minus sign because it was minus c. And then the 2 remaining terms, and then what they all had in common. So there's my second derivative. We made the Schrodinger equation look so pretty. That didn't come out pretty. So there's our second derivative. And that second derivative should be equal to c squared minus kappa times e to the minus c squared over 2. Now I can't take the, c squared minus kappa is approximately equal to c squared, because this is the full-on solution. This is going to be the correct one. So with this equation, notice that these have a h, so I can bring those to the other side of the equation and put them in there with the 2 terms already times h. So if I subtract c squared h from both sides, those are going to subtract out. Okay, Chad, you shook your head no, which I assume means you didn't quite follow.
I'm just not following where
Okay.
Oh, yeah.
So we have just, with our work down here, that gives us, oh, nice. If I could figure out how to do that intentionally, that would be good. So that gives us this term here for the Schrodinger equation. All the work down below was to take this derivative and convert it into that. And so now, according to the Schrodinger equation, the right side is staying the same, right? This is staying the same in both cases. I just replaced psi with he to the minus c squared over 2.
So we say that the h is taken in the place of the a from before. We had a linear combination.
No. H is that linear combination. So H is a lot more complicated.
Oh.
We're just writing H because it's a non-complicated way of writing the complicated formula. So I guess if you say it's taking this place, it kind of is correct because it is that thing. So just for a reminder, I'll write that at the top of the page here. H is equal to sum over j equals 0 to infinity, a sub j c to the j power. So H is all of that. You see this blowing up into a complicated problem, don't you? Yeah, yeah. Because you know what quantum physics generally is not? Straightforward. So now getting back to what I was saying. We're going to move this term in the red box over to this side of the equation, which means we just subtract it across. And in so doing, I'm going to have c squared h minus c squared h, and those terms disappear because they just subtract it out. Right, this term here and this term here, subtract out. I'm still going to have the minus 1. Here I had a minus kappa, so when I subtract minus kappa, it's going to become a plus kappa. So it's going to look like I just replaced my c squared with kappa. But really, I subtracted them across, so the right side, of course, is equal to 0 now because I subtracted across. Because if you look at it without realizing what was done, yeah, it looks like you just replaced c squared with kappa, and I don't know what happened on the right side. So this is our Schrodinger equation with a whole lot of work to get there. So it's still the Schrodinger equation. It's just a different version. For this to be true, either c has to be infinity. Well, we know that. That's how we found that solution. Or the thing in parentheses has to be 0. Right? If you have a times b equals 0, either a is 0 or b is 0. So that's what we're doing here. So now we're going to work with the stuff inside this parenthesis and say, for us to have a solution to the Schrodinger equation, this thing in parentheses must equal 0. And that did not change this. Now, this thing in parentheses had second derivative, first derivative, and no derivative of h. So now we have to work with h. So here h is written again in its full glory. And then we take the derivative of h. So taking the derivative, it's a summation. It seems like this is hard, but it's not. When you take the derivative of anything raised to a power, you bring down that power and decrease the power by 1. So that means no matter what j is, I'm going to bring down a j, and then it's going to be c raised to the j minus 1. So there's the derivative. And now comes the next tricky step. How in the world do we go from here to here? How is that even possible, you ask? Well, what we did, I like to introduce an intermediate variable. I say, let's let j equal k plus 1. Oh, did I write that? So if I do that, I would have k plus 1 equals 0 down here for my limit. And I would have, instead of j, I'd have k plus 1 here. Instead of j there, I'd have k plus 1. And instead of j minus 1 there, I'd have k. And then when you rewrite that, you come to you're going to have exactly what we have here. Then we just change k into j to get back to this. But there's one thing that doesn't seem to track until you think about it carefully. The thing that doesn't seem to track is if I change my j index or j to being 1 bigger, what happened to the first term? Because I'm starting at the same place. And the key to that is, if j is equal to 0, what is this derivative equal to? 0. And so we really only need to start at j equals 1. So with that substitution that j is equal to k plus 1, then I'd start with k at 0 to start with j equals 1. Because the j equals 0 term was 0. Looks like that didn't quite make sense to you. Well, let me do it out in long form then. That's what you get when you expand that out. And so with the with the second form, with this form here, your first term is going to be 0 plus 1, a to the 1, c to the 1, and then it would be 1 plus 1. I guess I should put a third term here. And so you see this term here was identically 0. And that identically 0 term is not showing up. But all the other terms are showing up exactly the same. So we dropped off the one that's identically 0 in shifting the index. So that's what we've done. We shifted the index by 1. So that's the first derivative. And then if we want to do the second derivative, well, I just did the derivative of the equation above in each case. And so if you take the derivative of j, a sub j, c to the j minus 1, you're going to bring down the j minus 1 and have the exponent j minus 2. Or, actually, I said I did the derivative of the one above. This here is not the derivative of the one above. It's this with the index shifted 2 spots. Why shifted 2 spots? Because it's going to be identically 0 for both j equals 0 and j equals 1. And so you can shift it over 2 spots because those first 2 terms are going to have zeros in front of them. And you're probably wondering, why are we shifting indices to begin with? Yeah, it makes sense to wonder. Well, here's a blank page. It's not supposed to be a blank page. See, it's not a blank page. Who knows why it showed up as a blank page? So here is what we found for our Schrodinger equation. So we're going to focus on this thing in parentheses, and we're going to substitute in so that we have the same exponent. Well, that's not the exponent. The same exponent on c. So if we look at the first term has no c with it. So I'm going to want this one to be the one that has c to the j power. So I look over here for the derivative, and this one here has c to the j power. So I'm going to, wait, no, that's second derivative. Whoops. Second derivative, this one here has c to the j power. So I'm going to substitute that in. So I have c to the j power. And so looking at that one, I have sum over j equals 0 to infinity, j plus 1, j plus 2, a sub j plus 2. So j plus 1, j plus 2, a sub j plus 2, and then we have summation at the front. Now my second term, I have the dh dc times c. So that means I want to have my derivative to have c to the j minus 1. So when I multiply it by the c, I'll have c to the j. My goal is to make sure I have c to the same power in each term. So that means I'm going to take this form, because that has c to the j minus 1. When I multiply it by c, I'll have c to the j. So I'm going to have j a sub j and this 2 is the 2 there. And then for the final one, I just put in the original function. So I just have a sub j, c to the j. So now all of these have the same c to the j power. Why do I want that? Because now what I've taken is this equation. I said the stuff that's in parentheses has to be 0 for the whole thing to be 0. Now I have this, and I can say, well, the stuff in this parenthesis has to be 0 for the whole thing to be 0, because c to the j isn't going to be 0 unless c is 0. That's the trivial solution. And then, of course, e to the minus c squared over 2 is 0 at c approaching infinity. As long as we're not limiting ourselves to trivial solution or c is at infinity, we're going to have this thing in the middle is 0. And yes, I saw Erin look at the clock, and she's right. It's time to stop. This gives us a relationship. Yeah, it's time for my pen to stop writing anyway. Gives us a relationship between those a sub j parameters. And we're close to finishing. We'll finish this up on Monday.